All right. So real quick review again. What's this group? What's this block called right here, over here on the side? S block, very good. What about down here? F, and then we're here, P, and then lastly, D block. Awesome. Today, we are going to be venturing in to the remaining two blocks, the D block and the F block, okay? But I want you to look at this screen up here, okay? You notice that we go from S to F to D to P, okay? And we're going to continue just doing it as we did on Friday, like a typewriter, okay? So when you get into the 4S, or the fourth energy level, okay, you notice as you go from 4S, it's going to be easier to do it on with this one. Let me zoom in here. So you notice, that's too dark. All right. So as you go from 4S, you immediately come into contact with the D block. Okay? Now, the values for D block are N minus 1. So if you want to write that on your periodic table that you can write on, do so. Okay? D block values are N minus 1. So that means when you are in this fourth energy level, you go 4S2, 3D1. Okay, then you go all the way back over here to 3D10. We're at zinc. And then you get back into the P block, which now goes back to the normal one of 4P. Okay? Now, if we're in the fifth energy level, we have 5S2. What's my value for D? 4D. And then if you go all the way through 4D10, then you get into the P block. What is it? Back to 5. Very good. Now, that's the D block. F block is N minus 2. Okay? So, again, going back to this slide, you're going to encounter the F orbitals before you encounter the D orbitals and then the P, okay? So, it's just going in order. So, if we are down here at the 6th energy level, we actually go 6S2, 4, F, there's 14 here, and then back to lanthanum of 5D, and then 6P. So if we're down here in the 7th energy level, we have 7S2. What's my value of F? 5, very good. So then you go 5F14. You can't see that. 5F14. Back to here. And really, since we're on the last one, you're only going to be able to go so far. Okay, basically to the end here. Because, and this is an older periodic table, 1995. The one up there on the side by the fume hood is a 2013. And as you see, we have since filled in. So you will have, I will get you, see if I can't find you a newer, updated periodic table. But a lot of times we don't even mess with elements down here, okay? So we're usually pretty clear, like out of the blue on that one. All right. So back to the notes here. So we fill orbitals in increasing order of energy. Different blocks in the periodic table are shaded. We've already done that. Let's look at this question. Now, this is a little different type of question. It's a good question, though. It says, what is the characteristic valence electron configuration of elements in group 7A, which is the halogens? Okay, so group 7A is right here with fluorine, okay? So let's go ahead and do fluorines, okay? Electron configuration, okay? So again, we started our home base of hydrogen, and that we start off with 1s, and then we start to count. 1, 2 to helium. We're at the end of the row. What do we do next? We ding. We go back to the left and down a level, right? So first we have to say 1s2. That brings us to lithium. We're in the second energy level, and we have not gotten to fluorine yet. So we just continue to count. Every time we come into a new energy level and or block, we start our counting over. So we get to 2s2. We hop across the ocean. We're still in 2, but what block are we in now? P, very good. 1, 2, 3, 4, 5 is fluorine. So that is what fluorines would be, okay? Excuse me. But that really doesn't answer our question, okay? Again, we're looking for the characteristic electron configuration for the halogens themselves, okay? So again, one thing we could do is we could do chlorine's electron configuration, okay? But one key thing is this term valence electrons, okay? Does anyone know what a valence electron is? Nope. The valence electrons are the electrons that are in the outermost energy level, okay? So you see that the largest energy level for fluorine is 2. So that means that these electrons and those electrons are in the outermost energy level. So those 7 electrons are in the outermost energy level. So these are your valence electrons. And as we'll see here in chapter 8, these are the electrons that are really used for chemical bonding. Okay. One thing that I want to introduce you to now is the condensed or electron configuration, or sorry, condensed or noble gas electron configuration. Okay. So what I'm going to do is, yes, even though this is a fairly small and short electron configuration here for fluorine, we can still reduce it. So what you do here is first identify your element in question. It's right here. You then go up a row and all the way to the right until you get to the noble gases, which is right here. And you see that helium is the previous line's noble gas. So what I'm going to do is I'm going to put in brackets, it must be in brackets, HE. You know, in math, when you use a letter to substitute in for a statement or some values, that's what we're doing here. We're simply using the previous noble gas as a stand-in for all the, like, everything else before the valence electron. So this helium, in this case, is standing in for that 1s2. So to complete this noble gas configuration, I simply just finish writing what's left here. 2s2, 2p5. And that would be my noble gas configuration. Again, in an instance like this, it really doesn't shorten anything up, other than it might save you a few seconds in counting. Okay? Let's look at chlorine. Okay? Let's look at chlorine. Let's do the longhand version first before we do the shorthand version. Okay? So again, we start our home base for longhand version. We do 1s2. We're at the end of the first row. We go 2s2. And we find chlorine is actually in the third energy level, so we got a little ways to go. So we go 2s2, hop across the pond, 2p6. That brings us all the way over here to neon. Still not where we need to be at chlorine, so we got to go back to the beginning again. Next, we're at 3s2. Okay. Hop across the pond, and then we get to 3p5. So just by going down one row, we've added a significant amount more. Okay. Can anybody tell me, when we're at chlorine, what the previous noble gas would be? Neon. Very good. It is right here. It is up one row and all the way to the right. So the condensed version will be in brackets, Ne, close your brackets. And again, as you see here, chlorine is found in the third energy level. So that means that, again, this electron and this electron, or electrons, I should say, are your valence. And neon now represents everything that comes before those valence electrons. So I substitute in my noble gas, and I get 3s2, 3p5. So looking at the condensed electron configuration between fluorine and chlorine, do you see some sort of pattern? What's that? Keep the highest energy level. But when I write it like this, you notice that both end as S2 and P5. S2 and P5. You see that? Yeah? How do you think bromine's going to end? S2 and P5. Okay, just different energy level. So in a question like this, where it says a characteristic valence electron configuration, it's really the best if you do these noble gas configurations. And so for the halogens, a characteristic, you can't see what I'm writing. A characteristic, goodness gracious, valence electron configuration would be this. NS2, NP5. Can anybody tell me what the N's stand in for? Just stands in for energy level. The noble gases will all have the same valence electron configuration, S2, P5. And so we put the N's in here just to represent any energy level that we might need, okay? So that is your answer for that sample exercise, NS2, NP5. Now let's look at the practice question down here towards the bottom. Which family of elements is characterized by an NS2, NP2 electron configuration in the outermost shell? Okay. So NS2 and P2. Okay. So let's think about it. Okay. We can pick basically any energy level here. That's why we have the ends. But let's keep it simple on ourselves. Okay. So we know that we're going to end on the second element in the P block, but we need to know what group number it is. Okay. So let's just go. S1, S2, hop over the ocean, P1, P2. Can we tell you what group number that is? It doesn't really have a name for a family. This would be, someone say it, I think. I heard someone say it. Group 4. Group 4 has a valence electron configuration of NS2 and P4. So again, don't get caught up on the ends. Just pick a row and just count like we have been doing. 1, 2, 1, 2. What about NS2 and P6? Noble gases. Or you could also say group 8 if you wanted to, but noble gases is the family name, so it's easier to say that. Does anybody need to see how we got that? So again, NS2, NP6, pick a row. 1, 2, S. 1, 2, 3, 4, 5, 6, which lands me on neon, in this case, neon, which is a noble gas. So let's do some more configurations. Okay, up here under sample is based on its position in the periodic table, write the condensed electron configuration for bismuth and how many unpaired electrons does it have? Okay, first and foremost, let's locate bismuth. It said it's element 83. So we are right here. Okay, we are way down there. Okay, so we are to do the shorthand or condensed or noble gas configuration. Okay, so we locate bismuth and we identify who the previous noble gas is. Who would that be? Xenon. Very good. Just go up above bismuth and to the right all the way, you get xenon. So in brackets, you put the symbol for xenon as Xe. And again, xenon is going to stand in for all of this before it. So now, xenon now becomes my home base. Okay? So I start at xenon, and you know xenon's already at the end. So what do I have to do? I have to, ding, go down all the way back to the beginning. Okay? And so I'm going to start with 6S. Okay? Now let's count. 1, 2. All right, so 6S. I'm trying to make this a little easier so you can see it all. Okay. Now, where have I just landed? Not the D block, F block. So what is my next number going to be? If I'm in the 6th energy level, what's my next number going to be? 4. 4, F, and just count. And I've already told you to write down how many F can hold, but let's count anyway. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Have we got to our destination yet? No, so 4F14. Okay, I'm at the end of the F block. I'm not at the end of an official row, but I'm at the end of the F block. So I go S to F to D. But what's my D value going to be? 5. Okay, so now I'm back here. Nope, you can't see that. I'm back at lanthanum. Count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Am I to my destination yet? No, I am not. So, but, oh, I didn't even write the thingy. 5D10. Okay, so here I am at Mercury. Then I cross into what block? The P block. But what's my energy level this time? I'm back to the 6, back to the normal. 6, 1, 2, 3. So I get XE, 6S2, 4F14, 5D10. I did it again. P. Say it, I must forget to write it. So that would be your condensed or electron configuration right there, a noble gas configuration. But that doesn't answer all of our questions. It says we need to determine how many unpaired electrons this has. So best way to do that would be to do an orbital diagram. Okay, so how many boxes does S get again? 1. Okay, and don't forget, bring down the label of 6S. Okay, now F, how many, take a guess at how many it gets? 7, very good. And it's going to be difficult to write this, I'm not going to lie. 1, 2, 3, 4, 5, 6, 2, 3. One more. Okay, for F, how many does D get? 5. 5, and then back to P gets 3. I'm really stretching myself here on the space. Did not plan accordingly. So again, don't forget 5D, 6P. How many electrons are going in the 6S box? 2. 1 up, 1 down. How many are going in the 4F total? 14. But again, get in the habit of doing each one getting an up arrow first, according to Hund's rule. Okay, once everyone has one, go back to the beginning of the F and put the down arrows. Every box so far has 2, so that allows me to go into the next one. Again, I've got 10 electrons I got to deal with. Put all ups first. Once everyone in the D block has it, go back to the beginning. Put down arrows. And lastly, my 6P has 3. So again, everyone has to get one first. I've now used all of them. How many unpaired electrons do you have? You have 3 unpaired electrons right here. You can't read that. It's supposed to say unpaired. Ran out of room. So one of the things you want to remember is give yourself plenty of space. Okay? All right. Let's look at our next example here. Okay. So we've got 2 elements here. We're going to do the first one together. And then I'm going to have you do one of them on your own. So let's do A, cobalt. Okay? It is element 27. They're so nice, they tell you what element it is. So cobalt is right here. Okay? What block is it home in? D block. All right. So it wants us to use the condensed version. So what element am I going to use? Argon. You can't see that. Okay. Argon. So argon now becomes our new home base. Okay. Right here. And so I'm at the end of the row. So I just continue on going. We hop into energy level 4 with potassium, 4s. Now we begin. 1, 2, 2. Then I'm entering the D block. What's my energy level value for D block here? Is it 3. Because we're in, it's D is n minus 1. We started in the 4th energy level, so that makes this 3. So then we count 1, 2, 3, 4, 5, 6, and 7. 3, D, 7. And that's your answer for cobalt. What I want you to do is the element tellurium, which you can find all the way down here as element 52. Okay, again, doing the condensed version. And then we'll talk about it before we start to wrap things up. All right, is everybody done? Okay, what noble gas element am I going to use? Krypton. Okay, and so as a class, take me through it. What do I write first? Okay. Continue on. 4D what? 10. Very good. And then not 6P, 5. The S and the P are going to always be on the same energy level. Okay? You said 4. And that's it. So far, we've done orbital diagrams, a longhand version of electron configuration, and shorthand version of electron configuration. Now, just a few more notes that I want to talk you through before we wrap it up. And that is the fact that there are some irregularities that occur when there are enough electrons to half fill s and d orbitals in a given row. Okay? And so what these irregularities do is, if we look at copper, okay? Copper is right here, okay? Normally we would think this would be like 4s2, 3d8. But, actually that's supposed to be, I think it says 8. I can't tell if that says 8 or not. No, sorry, 9, 3d9. But its actual configuration is 4s1, 3d10. And it does this so that we can have more electrons in a farther out energy level. Because the more energy level or more electrons you have out in the energy level, typically the higher energy you are. And like as I mentioned last week, that's not usually the best thing for atoms. So the 4s and 3d are very close in energy. That's why they can kind of get away with the Okay, you can have 10 in your D. I'll just have one in my S. No biggie. But this doesn't occur only in the D block. There are some that occur in the F block as well. I try to avoid giving you questions that deal with these anomalies because you'd have to memorize it and everything like that, and I just don't want you to have to put that on your plate. So just know that there are some weirdos out there in terms of electron configurations that, based off of energy values, kind of don't obey the rules every single time. So go ahead and put your stuff away. That wraps up chapter 6. And I am going to try to stop the recording.